So today we'll cover MOSFETs, bit of the construction and the operation of the device. All right. So we spoke briefly about MOSFETs. Stands for metal oxide semiconductor. It's a sandwich layer built on a P or N-type substrate. That's the semiconductor. Then we have an oxide or an insulating material, and we have a metal gate on top. Okay. So the structure in the center is we're going to focus on for the next slide and for this one. Okay. This forms, what does it form? If you have two conductors separated by an insulating material, it's a capacitor. So this is known as a MOS capacitor. So MOS capacitor. So what we're going to look at is the operation of this MOS capacitor and what it does before we look at the workings of a MOSFET. So there are three regions of operation for this MOS capacitor: accumulation, depletion, and inversion. Shortly stated, accumulation is where it accumulates charge carriers. Depletion is when it gets devoid of charge carriers, and inversion is where it actually the charge carriers invert, meaning if it's a positive charge, it inverts to a negative charge, and if it's a negative charge, it inverts to a positive charge. And the key thing here is this is different from the JFET. Okay, in the JFET, a channel was already existing. You manufacture a JFET, a channel is already present in the device, right? Remember, we had to apply a negative voltage at the gate to actually turn it off. Turn it off means to close the channel pathway. In a MOSFET, a channel does not exist, at least not in this one. We must apply an external voltage or an external source of energy to create a channel. Okay, like any two-channel device, FETs, whether it's JFETs or MOSFETs, we have two ends, two terminals, drain and the source. A channel needs to exist between the drain and the source. So when you apply a voltage between the drain and the source on either side, current can flow through. In this kind of MOSFET, a channel does not exist. So we apply an external voltage. And so these three stages of operation will create that channel. Okay. So in this case, we have a P-type substrate. We have a metal gate at the top, right? Metal gate. And I believe also mentioned, typically nowadays, instead of being made of metal, the gate is made of polysilicon. Polysilicon is a form of silicon. The name comes from the fact that it's not a single crystal silicon. All silicon wafers that we work with are single crystal. Polysilicon means it's polycrystalline. You need to go back to chapter 1 to remember what I'm talking about. Chapters 1 and 2. Okay, so instead of metal, nowadays it's polycrystalline silicon. All right, and then we have the oxide layer separating the two. So silicon dioxide. So you apply a gate voltage, and that gate voltage is far less, or it's negative with respect to the source and the drain. When you apply a negative voltage across this thin oxide layer, what happens? Negative charges in close proximity to positive charges. Opposite charges attract. And so there is a collection of positive charges or holes that accumulate right below the oxide layer, close to the surface. Okay, close to the surface. This layer is very, very thin. So it's a very thin sheet of layer. Okay. Now, as the gate voltage is made increasingly positive, you increase the voltage. Right now it's negative, but you're increasing the voltage. At some point, at some point, the junctions get reverse bias. Okay. The junction. Hold on to your thoughts. The other junctions are reverse bias. The drain and the source junctions are reverse bias. Okay. So here, as the voltage turns positive, now instead of negative charges, now you have positive charges. So what happens then? Again, the same thing, right? Opposite charges attract. So if gate voltage is turning positive, it attracts the electrons. Sorry, it repels the holes and attracts whatever little electrons were there towards the top surface. It is still not sufficient to create a channel. Okay, so a channel still does not exist. Not yet. So again, when you first apply a negative voltage, you're accumulating charge carriers. So it's positive charges that are accumulated over there under the surface. As VGs increase and turns positive, it repels the positive charges, goes back into the P-type material. It attracts some of the electrons, but more importantly, if it repels the holes, what is left behind are the ionized atoms. Remember, ionized atoms. P-type material is created from acceptor atoms. 3 electrons in the outermost orbit. So it's one extra positive charge. The electrons are going away, it leaves behind positive charges. And so a region forms here that now has negative charges. Okay, but these charges are from ionized atoms. They are not free to conduct. So they are depleted of free charge carriers. Hence, the name of the state is depletion. Okay. In the first one, where you accumulated positive charge carriers, they are free to move about. Okay, it's a very thin layer. It's a very thin layer, but they are still free charge carriers. When the gate voltage is increased, now the holes or the charge carriers are rejected from the surface or pushed away from the surface. So it's now depleted of free charge carriers. All that's left behind is the negatively charged ionized atoms. They are not free to move about in the lattice because they are part of the semiconductor lattice. So that's the key thing. So it's depleted of charge carriers. If there are no charge carriers, you cannot conduct electricity, or you cannot conduct current. Does that make sense to everyone? Okay. There's a lot of stuff going on. Yes. That's still to come. Yes. That's the next state. Not quite. All right. Any questions? So far, so good. Okay. So now VG is still increasingly positive. Still increasingly positive. At some point, it's going to cross over or it passes a certain voltage. And at that voltage level, it's going to attract a lot of free charge carriers. Okay. That voltage is known as the threshold voltage, VTN. It is also referred to sometimes in some books as VTO. And that's the point where the positive sheet layer turns into a negative sheet layer. And these are negative charge carriers that are free to move about and conduct electricity or conduct current. This region is probably the same, not probably, it is the same size as this one. Okay, so now have negatively charged electrons that are free to conduct electricity, they are free to conduct charge. And now at this point, the device has created a channel, or we have created a channel in that device by applying an external voltage. Okay, so 3 states or 3 regions of operation for that MOS capacitor. First is you're controlling the device. You're turning off the device by applying a negative voltage, so there is no channel. Okay. Second is you increase the voltage, so it's now depleted of charge carriers. Then you cross the threshold voltage. That's where the channel will form, and now the device is in a state of readiness. At this point, if we apply a voltage between the drain and the source, the electrons will drift in response to that electric field. Any questions? All right, so let's take a pause, think over that. Let me know if you have any questions. Yes. Yes. Positive voltage. Because this is a P channel. Be different, yes. Not be reverse bias, but opposite voltage. So again, the key difference between a J-FET and the MOSFET is the J-FET is a depletion mode device. You must apply a negative voltage at the gate to turn the channel off, basically turning the device off. Channel is already existing in a JFET. In a MOSFET, a channel must be created. Okay, must be created. And so the creation of the channel goes through these 3 states. Again, when we get into the device operation, of course, it's far more complicated. There's tons of equations. The capacitor itself is not just a single capacitor. There's 2 capacitors in there. One is basically the physical capacitance that is present because of the gate separated from the semiconductor. And the second one is because of the charge accumulation. So there's an oxide capacitance, and there's also voltage dependent capacitance. Okay. So a NMOS transistor construction is shown in here. This is a P-type substrate. The substrate is marked as either B for body or bulk. So body or bulk of the structure. It can also be sometimes refers to as the substrate, but again, we use S for source. So if you see B in a MOSFET, it is standing for the substrate or the body or the bulk of the device. Okay, this is a NMOS transistor, which creates an N-type channel. And so we have a P-type substrate. We have heavily doped N regions right here. The plus, if you remember, simply indicates it's heavily doped. So we use plus for heavily doped, and we use plus plus for extremely highly doped. Extremely heavily doped. But both the source and the drain are the N plus regions in a P-type substrate. Theoretically, this device, like the JFET, can be symmetrical. Okay, you can use the drain and the source, and vice versa. And then, of course, there's the gate region. There's an oxide layer right here that separates the gate from the bulk. Okay. Now, the drain and the source regions are always reverse bias. So they're kept at reverse bias with regards to the bulk. So drain and source are reverse biased with respect to the body of the device. Okay. So to ensure that only a small leakage current would flow through, because you have an N plus you have an N type region and you have a P type region. So you have a diode between the drain source and the body of the device. Right? You have two diodes. You forward bias them, you have internal currents flowing through. So we don't want that. That would interfere with the operation of the device. So we keep these junctions reverse bias. Okay. The channel region, of course, is between the two N type regions. Now, again, it's an N type region, so we need a N type channel if you want to have current flow. So we go through the process, we apply a negative voltage, VG, VS, and VD are negative with respect to the body. Then let's see device operation at that point. So in VGS is far less than the threshold voltage. Okay. Then all we have is basically depletion regions between the N and P type material, right? So there's depletion regions right here. Device is currently off. There's no channel that exists for current flow. When VGS increases, but it's still less than the threshold voltage, right below the channel, we have this depletion region that develops, and it merges with the depletion regions that were present in the device. Okay. So here, the depletion regions merge. Okay. And now, third case, where VGS crosses the threshold voltage, inversion occurs. Now you have a thin, right? Channel of charge carriers that are free to move about. Okay. This is a common point of confusion. So when students are learning for the first time, and when I was learning for the first time, I see negative in there. So I think, okay, a channel is already existing. And then I see what's the point. But again, the key thing is this is immobile. They are not free to move about. They're immobile charge carrier, not charge carrier, sorry, immobile acceptor atoms. Okay. So that's the negative. But they are not free charge carriers. They don't move about. The channel is free charge carriers of electrons that are free to conduct. They're free to move about. So that's the difference. So you have an entire region of negative charges. There's a very thin sheet underneath the oxide layer, right? At the surface of the substrate that is free to move about. And now when you apply a voltage between the drain and the source, these charge carriers can drift or can move in response to the applied electric field. Hence the name, field effect transistor. So you're now controlling the flow of electrons between two terminals via the gate, via a three-terminal device. Okay. All right, let's take a pause. Let me know if you have questions. No? No understand. Unassigned reading. BJTs, bipolar junction transistors. MOSFETs technically actually are not part of the original curriculum, but I think all instructors do a little bit of the MOSFETs. You'll do digital logic circuits and analog circuits in 307, 308, and that's where you'll need an understanding of the MOSFET. Over the years, going on a little bit of tangent, there was a MOSFET experiment that was part of 306 for a few years. And then from what I understand, this was in the 80s and the 90s. And then they created the 307 course, or maybe it was already in existence, and they moved the MOSFET into the 307. So 307, you'll be dealing with MOSFETs all through. And even in 308, I believe the analog circuit design is all using MOSFETs. Some BJTs, some MOSFETs, mostly MOSFETs. So again, it's an important topic. I'd like to devote at least 2 or 3 classes to it. Okay. So again, key takeaways: MOSFET. This is not a depletion mode device. A channel does not exist. We must apply an external source or external voltage to create a channel. In a P-type in a N-channel MOSFET, we start with a P-type substrate. In a P-channel MOSFET, we start with a N-type substrate. The operation is exactly the same, except everywhere else it's reversed. P is replaced with N, N is replaced with P. So for an N-channel MOSFET, we start with a P-type substrate, implant 2 N-type junctions or N-type regions right here and right here. Those are the drain and source. The current between the drain and source is controlled by a third electrode, which is the gate. The channel must be created. In this case, we use the MOS capacitor to create the channel by applying a voltage at the gate terminal. The gate terminal in an N-type MOSFET creates an N channel, a thin sheet layer of free charge carriers of electrons. And then when you apply an electric field between drain and source, current can flow through, or the electrons drift, move in response to the external electric field. Okay. So I'm going to end class here today, and then we'll pick up here again on Wednesday. Comments? It is a lot of things going on. Yes. Uh-huh. Uh-huh.